Hi, we are going to talk this time about using the Laplace transform to solve a differential equation with a discontinuous forcing function. So in the last lecture 6.3, we got some tools for dealing with setting up discontinuous functions using the unit step function and then knowing how to take the Laplace transform. Now we're going to go through a complete example of solving an initial value problem with a discontinuous forcing function. So here's the equation right here. Uh, Second order constant coefficient, ordinary differential equation with a forcing function there. We've got initial conditions here, and then we've got a description of the function g of t right there. So g of t is basically a constant force applied for a finite period of time. It looks like this. Nothing much is happening until time t equals 1, and then there is a force applied between 1 and 4, and then the force is removed, and that we're done. Okay, so actually there should not be a vertical line here. There's no vertical line. So it's basically a constant force applied for a period of 3 seconds. There's the time. Okay, so what we're going to do is solve this differential equation and then see what the solution looks like in a variety of time intervals. In this time interval, what the solution looks like, what the solution looks like in this time interval, and then what the solution looks like in the time interval after t equals 4 seconds. Okay, so first thing to get clear is a bit of terminology. That is capital G of S. That is going to be the Laplace transform of g of t. Okay, so in order to solve this initial value problem, we are going to, step 1, take the Laplace transform of both sides. So we're going to take the Laplace transform of the differential equation. Take Laplace transform of the differential equation. Okay, so we do that on both sides. What are we thinking in the background while we're doing this? Well, we know that I'll just make maybe note of that over here to the side, that the Laplace transform of y of t, that is the function which solves this differential equation. We know that is a function of s, and we are going to denote that by capital Y of s. Then the Laplace transform of the derivative will be s y of s minus y of 0. And that's what makes this transform so powerful in solving differential equations, is that the Laplace transform of the derivative is related to the Laplace transform of the function in a very simple way. Similarly, the Laplace transform for the second derivative, we can represent that as in this manner here, s squared times capital Y of s minus sy of 0 minus y prime of 0. Okay, so we have a clear relationship between the Laplace transform of the function and the Laplace transform of the derivatives. Then we can take the Laplace transform on both sides of the differential equation, and what we will get is this here. We will get s squared plus 2s plus 37 times capital Y of s minus sy of 0 minus y prime of 0 plus 2y of 0, and that will be equal to the Laplace transform of the right-hand side of the differential equation, and that is g of s. Then step 2, we apply the initial conditions. Apply the initial conditions and rearrange. Okay, so in this case, the initial conditions are 0, which makes the algebra nice and easy. So this thing here, that is 0, this here 0, this here 0. That is a result of these initial conditions. sitting right here. We know that y of 0 is 0 and y prime of 0 is 0. So now we've applied the initial conditions and rearranged, and that gives us this expression here for capital Y of S. So capital Y of S is the Laplace transform of the solution to the differential equation. As usual, our objective is to find what function satisfies the differential equation. Okay, actually, as of yet, I haven't made use of the fact that I know what g of t is. I mean, this so far, this statement here is true for every differential equation, y double prime plus 2y prime plus 37y equals g of t, regardless of what g of t is. Okay, so now I'm going to determine g of so now that I'm here, I'm going to determine g of s, which is the Laplace transform of g of t. In order to do that, I want to write g of t as some combination of unit step functions, because I know what the Laplace transform of the unit step function is. So I'm going to do that. I'm going to write g of t is equal to u1 of t. Okay, so we come along until time t equals 1, and then we our value of our function is going to be 1. Then we're going to go along until time is equal to 4, and then our function is going to go back down to 0, so we need to subtract u4 of t. We did this in the previous lecture as well. So you need to be able to form expression for g of t in terms of the unit step function. That's going to allow us to easily compute capital G of s. We could use the table, or we could use the integral. We could take the integral, the improper integral that defines the Laplace transform, or we could look in the table. So either way, we're going to get this expression here for capital G of s. Okay, so the e to the minus s is over s is the Laplace transform of the unit step function at 1, and e to the minus 4s over s is the Laplace transform of the unit step function when c is 4. Okay, so now we have a complete expression for y of s for this precise differential equation that we had here. It looks like this: e to the minus s minus e to the minus 4s divided by s times s squared plus 2s plus 37. Okay, so now we need to find the inverse Laplace transform of this guy here. That looks a bit daunting at first sight there, but let us break it down into steps. First of all, we would be able to find the inverse Laplace transform where those e to the minus s and e to the minus 4s not sitting there in the numerator. So let us just from that say, let us take a look at just the denominator of that fraction. It looks like this: s squared plus 2s plus 37. And let us see if we can find the inverse Laplace transform of that. So that would be, in fact, well, I'll just define that to be little h of t. So that's going to be the inverse Laplace transform of h of s. Okay, you can see that probably partial fractions is going to come into play here. Before we do that, let's take a look that let's notice that what we actually want out at the end of this whole thing is y of t, and that's the inverse Laplace transform of y of s. Okay, and what does that look like? Let us take a careful look at this here. What does that mean when we have that situation? What does it mean when we see an exponential times something here? That means that y of t is going to be u1 of t times h of t minus 1. That is coming from this one here. And then it's going to be minus u4 of t times h of t minus 4. So this is the backwards direction of the so when we said what happens when we have a delayed forcing function, that the Laplace transform is the exponential times whatever Laplace transform we had. This is going backwards on that same idea. Okay, so this is this statement here that I'm sort of separating out this part here, this h of s part, because I know that what the exponential does is basically cause a shift in the time domain. So let me just clarify which formula that is on our formula table. So this is formula 13, and that formula 13 is telling us the Laplace transform of uc of t times f of t minus c is equal to e to the minus cs times f of s. Okay, that is what formula 13 is telling us. And what I have just done here is use it in a sense, if you like, in the backwards direction. I am recognizing that I have something like this, that is this, and I'm saying, okay, I'm going to go backwards this way. Okay, so it's important to be able to use the table to your advantage as you're being able to try to find these things out. So now when I look at where I'm going, I've simplified my problem quite a bit, because in order to get y of t, I only now have to figure out what is h of t, because then I will be able to substitute t minus 4 and t minus 1 into that, and I will be able to combine the whole thing and get the final solution. Okay, so now I have the problem of determining h of t. So I'm here, h of t, that is the inverse Laplace transform of 1 over s times s squared plus 2s plus 37. That is the problem that I need to solve. We'll use partial fractions. Okay. This should not come as a surprise at this point. We will use partial fractions, but notice that s squared plus 2s plus 37 does not factor over the reals. Okay, it has complex roots, so you can check that by just using the, for example, b squared minus 4ac, and seeing that you'll get a negative underneath the square root sign. So we have to recall then, I think this may be the first time we've done this so far, that the partial fraction decomposition of an irreducible, when you have an irreducible quadratic, looks like this. So we've done, I think, linear factors, possibly even repeated linear factors. This may be the first time that we've seen an irreducible quadratic. And the proper way to do the partial fraction decomposition here is a over s plus b s plus c all over s squared plus 2s plus 37. Okay, you'll maybe as a memory aid, you'll notice that this denominator here is degree 2, and then this is degree 1. The numerator is 1 degree less than the denominator when you set up the partial fraction decomposition. Similarly here, if these are not repeated factors. Similarly here, this is of degree 1, and then this is of degree 0. Then we do the usual partial fraction method of finding a, b, and c, those constants, and that will be a times s squared plus 2s plus 37 plus s times bs plus c must be equal to 1. Okay, so I'm basically saying that the denominators are the same, therefore the numerators must be the same. That's how I do that. And then I can observe which terms are a squared s squared terms. So I'm matching these coefficients. Those are the two terms that have an s squared in them. Therefore, and there's no s squared term over here. Therefore, a plus b must equal 0. Next, I look at the linear term, and I see that there's a linear term here, 2as, and there's a linear term here, s times c. So then I notice, and there's no linear term over here. So again, that must be 0 on that side. And so I've got 2a plus c has to be equal to 0. And then I look at the constant term. I have a constant term here, and there's no constant term here, and then there's a constant term there. So I get that 37a has to be equal to 1. That means a is 1 over 37. That means b is minus 1 over 37. And that in turn means that c is minus 2 over 37. Okay, so I've managed to find the partial fraction decomposition for h of s, and it looks like this. H of s is 1 over 37 over s minus 1 over 37 s plus 2 over s squared plus 2s plus 37. All right. The inverse, now I'm in a situation where I'm trying to use the table as best I can to get from here back to h of t. So this one, let's take a look first at how we're thinking of this term here. That's going to be thinking that the Laplace transform of 1 is 1 over s. Okay, so therefore the inverse Laplace transform of minus 1 over, sorry, not minus, 1 over 37 over s, okay, that's going to have to be 1 over 37. Okay, because this is, I mean, it's a linear operator, so I mean you could also be thinking this in fact if you liked as 1 over 37 times the inverse Laplace transform of 1 over s, which I've just identified from the table as being 1. Okay, so that's going to take care of this first term over here. Now we need to worry about this term here. We can easily multiply this in afterwards, but let us get a handle on what's happening here. So it's s plus 2 over s squared plus 2s plus 37. So let's just write out what we're considering here. Consider s plus 2 over s squared plus 2s plus 37. Okay, that's what we're considering. And we look at the table, and let us think what might occur to us to take from the table that is going to be useful. So that would be, for example, the Laplace transform of e to the at sine bt, that one there, that Laplace transform that is equal to b over s minus a squared plus b squared. Another one that might seem to be coming in useful would be e to the Laplace transform of e to the at cosine bt, and that is s minus a over s minus a squared plus b squared. Okay. All right. So I have these things either sort of at my fingertips in my memory, or I'm looking them up in the table, and then I'm gonna look over it here and say, it's looking like, well, it looks like I'm gonna possibly get something like this because I've got s plus 2 in the denominator, maybe. Okay, then I think to myself, well, I need to have something plus something, something minus or plus something all squared here in the denominator. So what I'm going to do is complete the square. Okay, keep sort of track of these techniques that we're using because they're just going to be used over and over again. So complete the square. Okay, that is going to be s plus 2 divided by s squared plus 2s plus 37. And I complete the square, doing nothing in the numerator. And then I'm looking here and I'm thinking, okay, that is s plus 1 squared, because then I get s squared plus 2s, but then I only get plus 1. So that is 36 short, so I'll add that there. So I complete the square. Okay, now I'm looking at this thing, and I sort of feel like I'm getting where I might be able to make some headway, but I have a slight problem in that here you see s minus a, s minus a. And here I've got s plus 1 and s plus 2. So that it's not completely in the form that I need. So I'm going to fix that in this way. I'm going to say s plus 2. So going from the next step here, I'm going to say to s plus 2 is s plus 1 plus 1. Why did I pick s plus 1? Because the s plus 1 is already down here. So I'm going to rewrite this in this way. Um, s plus 1 divided by s plus 1 squared plus 36. Then I've got that additional 1. There it is. 1 over s plus 1 squared plus 36. I'm starting to get happier because I can identify what the um, what the inverse Laplace transform of this thing is. And this is, I'm now looking at the Laplace transform of e to the minus t cos 6t. That is basically the this formula we identified here, this one we identified here, that is with a equals to minus 1 and b equals to 6. Okay, then I'm looking at this one, and it's not exactly in this form that I see this b here, but I can easily fix that problem, and then I recognize this as 1/6 of the Laplace transform of e to the minus t sine 6t. I mean, you already have a fair bit of experience solving these second order differential equations. So when you see, for example, a cos 6t coming up, you should not then be surprised to also see the sine 6t. And also when you see the exponentials here and here. So you're kind of thinking when we were solving the second order differential equations that were homogeneous with constant coefficients, we would identify in the case of complex roots, and now we're sitting here with an irreducible quadratic, we would often we would often identify lambda as the real part of the root and mu as the imaginary part, and then we would see both the exponential and the sine and cosine function coming. So you can sort of use what you already know to guide yourself to um, how to solve these things. Okay, so now I can figure out what is h of t. H of t is going to be, make that a little bit neater. H of t is going to be 1 over 37 minus 1 over 37 multiplied by e to the minus t cos 6t plus 1/6 e to the minus t sine 6t. Okay, we're not quite finished because y of t is equal to u1. This is our answer right here. Y of t is equal to u1 of t h t minus 1 minus u4 of t h t minus 4. Okay, now this is a major pain, right? Because you have to write this thing out in this humongously long way. So in a test or an assignment or something like that, it is perfectly reasonable to leave your answer like this. You are welcome to leave the answer like this. Both pieces, of course. Answer. There's your answer. I will actually write out y of t without having it refer back like this, the h to something above, just this one time. But answer is fine like this. Oops, fine like this. Okay, so but let us just write out what we would do if we were just going to have the function y and eliminate h from this. We would end up with this thing here. It's a bit of a bear, but here it is. That would going to be u1 of t times, now this is going to be h of t minus 1. That's going to be 1 over 37 minus 1 over 37 e to the minus t minus 1 cosine 6 t minus 1 plus 1/6 e to the minus t minus 1 sine 6 t minus 1 minus u4 of t times this whole guy again with t minus 4. Okay, so that's 1 over 37 minus 1 over 37, and then all this multiplied by e to the minus t minus 4 cosine 6t minus 4 plus 1/6 e to the minus t minus 4 sine 6t minus 4. There it is. Okay, that's the rather long but full solution to this initial value problem. Okay, let's just have a bit of a discussion about the solution. Here's a plot of it. That's a plot of this function right here, y of t versus t. Okay, let's talk about the sort of different zones of behavior that we see. And I'm going to divide that into three different regimes, 0 to 1, 1 to 4. So 0 to 1 is going to be this area right here, 0 to 1, and then 1 to 4 will be this area right here, and then after 4. Okay, what's happening between 0 and 1? Both the initial conditions are 0, and the system is at rest, and no force has been applied. Okay, so we have u1 of t is 0, u4 of t is 0. This is only in this area here between 0 and 1. Both of those things are 0, and that is going to be telling us that y of t is 0. The system is just sitting there at rest. Nothing has happened. Okay, I'm going to call that, let me call this y1 of t, and it's equal to 0. Okay, then what happens is a force is applied, and the external force is equal to 1. During the time between 1 and 4, we have that the function we found, the function y of t, is a solution to the initial value problem y double prime plus 2y prime plus 37y equals 1. Up until time between 1 and 4, I mean, the differential equation, the forcing function is 1. And the initial conditions would be y of 1 equals y prime of 1 equals 0. Because we know from here that the solution is 0 until we get into t equals 1. Okay. So we could, in fact, solve this initial value problem here, which would be valid for this interval between 1 and 4, using our previous methods. We would use we would solve the homogeneous equation, then we would use perhaps the method of undetermined coefficients to account for this. Okay, so during this interval, what does the solution look like? It looks like this: y of t is equal to 1 over 37 minus 1 over 37. Here it is, e to the minus t minus 1 cosine 6t minus 1 plus 1/6 e to the minus t minus 1 sine 6t minus 1. There it is. Okay, this is, we don't have the rest of it because, I'm going to call this here y2 of t. We don't have the rest of it because u4 of t is equal to 0, t less than 4. Okay. So we haven't had that next step down that causes the solution to change. And then what happens after t equals 4? The external force is 0. So the solution to that differential, so the force is 0. So actually the solution in this area, the solution here is it is a solution to this differential equation, 2y prime plus 37y equals 0, right? Because the external force is now 0, so that is this guy right here is now 0. However, the initial conditions, what are they? y2 of t at t equals 4. So we can solve this differential equation in pieces if we like, or we can do it like we did on the previous thing. We solved it all in one piece. So let's take a look at this. This is what the initial conditions are when y of t is equal to 4. So that's going to be y2 of 4 and y2 prime of 4. Okay, so we can compute those. Oh, it's a little bit laborious, but not too bad. What we do is we just look up here. There's y2. We have an expression for it. We simply evaluate it at 4. We take the derivative. We evaluate the derivative at 4. Let me tell you what those numbers worked out to when I did that. Y2 of 4 is approximately 0.0263, and y2 prime of 4 is approximately minus 0.00623. Okay, so I can calculate those because I know what the function behavior is between 1 and 4. So now I have a differential equation, here it is, and I have initial conditions, here they are, and it's a homogeneous differential equation. This one is extremely easy to solve, and you will recognize this as an initial, this is an initial value problem for damped free oscillation. Okay, it approaches 0 exponentially fast for t greater than or equal to 4. Approaches 0 exponentially fast for t greater than or equal to 4. And we can see that in the graph that we drew of the complete function when we had the solution using the Laplace transform. In the area where t is bigger than 4, that is right here, we see that the solution is oscillating, but it is approaching 0 exponentially fast. All right, that it concludes section 6.4. That is differential equations with discontinuous forcing functions. Thank you.